Hello everyone. My name is Urvi Goyal and I'm a software engineer at Microsoft. And I welcome you to this part 2 of the 5-part series by Scalar where we are covering linked list data structure end to end. In today's lecture, we'll be looking at some medium level problems on linked list. So I hope you have covered the last lecture where I discussed what exactly is linked list and some of the basic operations on linked list. That would be important to cover that, to understand that completely so that we can start and solve some medium level problems. All right, starting with the first one. The first problem is given two linked lists, tell if they are equal or not. And when are two linked lists equal? They're equal if they have the same data and the arrangement of data is also the same. So for example, we have this input where we are given two linked lists. The output here should be 1. It's a typo, but we can see that these linked lists are they have the same data and also the same arrangement of data. So we can say that these two linked lists are equal. All right, now how do we check that? We can check that using two pointers. So we can create two pointers. One pointer would be here for list 1 and another pointer for list 2. All right, let us see like this. So I have one pointer here and I have one pointer here. Okay, let's call it head 1 and head 2, and we can just keep comparing the values of head 1 and head 2 of these two pointers. If at any point they become not equal, then that means that my two linked lists are not equal and I can return false. If not, I can just like keep moving forward. I'll check for the next elements and compare those. Okay, and till when will I keep doing this? Until one of the or both of the heads become null. So at some point, both of these pointers will reach null. Now it is important that both the pointers head 1 and head 2 reach null at the same time. For example, if head 1 reaches null but head 2 does not reach null, for example, here we have another element 6 after 5. At this point, of course, we cannot compare null and 6. So we'll just break the loop and we'll see that head 1 and head 2 are they both equal to null. Okay, so we'll keep checking, we'll keep traversing the two linked list until one of the pointer becomes null, and in the end we'll also check that both of the pointers should be pointing to the null at the end and not just one. Okay, so let's look at the implementation here. Let's create a function that returns a boolean value, bool check equal, and here we can expect two linked lists, basically two heads, and we don't need to pass the head values by reference because we're not actually making any changes to the linked list. We're just checking to see if they're equal or not. Okay, and that's why we can just use their head pointers to traverse the both of the linked lists. So we can keep the condition for the while loop till head 1 and head 2 do not become equal to null. Okay, this means that both of these are not equal to null. Till that time, we'll keep checking if head 1 value is equal to head 2 value, or let's say if head 1 value is not equal to head 2 value. If they become unequal at any point, then I can simply return false because that means these linked lists are not equal. Or else if they are equal, then I just need to move my pointers forward. So I'll say head 1 is equal to head 1's next and head 2 is equal to head 2's next. Okay, so at the end again we need to check that both of these pointers become null at the same time. So while returning, we can either add it as a condition, or we can just return the result of head 1 is equal to null and head 2 equal to null. Okay, so if one of these, oh, not and, we should say or, because we want both of these values to be null. Okay, so if only one of the values is null of out of head 1 and head 2, then these linked lists are not equal. If both of the values, head 1, head 2, not values, I should say the pointer values, are null, then that means that these two linked lists are ending at the same point and they are in fact equal. Okay, so let's create two linked lists here. So here we'll return, we can either add a if condition, or we can just return the result of head 1 equal to null and head 2 equal to null. So basically we want both of these pointer values to become null at the same time, and this will return true only if both head 1 and head 2 become null. Alright, so let's create our two linked lists here. And I'll just print the result of check equal, where I'll pass head 1 and head 2. So right now these two linked lists are equal, so it should return 1, but if I remove the last node of my second linked list, it will return me 0. And the time complexity of this solution would be O of n, where n will be the length of the linked list that is shorter. Our next question would be reversing a linked list. So if this is the linked list that is given to us, we have to reverse it. Not just print the reversed list, but actually reverse the links of my list. That means the list that should come out to be should look like this. This is the reverse link, where you'll see now 5 is pointing to 4, 4 is pointing to 3, 3 is pointing to 2, and 2 is pointing to 1. So you're understanding, we're not just printing the values or the list, or we're not just traversing the list in a reversed manner, but we're actually reversing the links of my list here. So how can we do that? Let's try to understand. Let's take a few elements, 1 2 3. Okay, let's take, we have these 3 elements in my linked list. Now if I am to reverse the list, that means I have to reverse the link. I have to reverse these 2 links, so that 2 points to 1 and 3 points to 2, and also 1 should point to null, right? So basically 3 links for these 3 nodes I have to reverse. So if we do this 2 at a time, for example, I say let's first take just these 2 elements, okay, and reverse this. I can do that by taking 2 pointers. For example, I take a pointer to 2, which is current, and 1, let's call this previous. Okay, and I say now what you do is you put current next as previous. So what will happen is this link will get removed, okay, and we'll have another link where 2 will be pointing to 1 instead of 3. Now if we do that, we have lost here the access to the rest of my linked list, right? How do I access the rest of my linked list after 2? Because now I have already changed the next of 2, so I don't have access to what was there previously. So I'll actually have to make use of 3 pointers here. Okay, if I can have another pointer before changing this link, if I create another pointer and let's just call it the next pointer and make it point to 3. In that case, even if I remove this link and reverse it, make it point to previous, I still have access to 3 through the next pointer. Okay, so we basically will need to have 3 pointers here. Okay, previous and current between the previous and current nodes we'll be reversing the link, and we'll be using next to see what will be our next set of previous and current nodes that we'll need to reverse. Okay, if you don't exactly understand yet what we're doing here, it's fine. Let's try to see with a proper example. But what I was trying to explain so far is that we'll need to keep track of the nodes with the help of 3 pointers. Okay, so let's take another example. Let's have 4 nodes here. Okay, so this is my linked list, and what I'll do here is I'll start with 3 pointers: previous, current and next. Okay, and let me start with my current pointer here on the head. Okay, this is my current head of my original linked list, and I'll make previous point to null, because you see, after I have reversed, okay, in the reversed linked list, the first node, the original head node, would become the last node of my linked list, and the last node of my linked list always points to null. Okay, so I have to make one point to null. So what we'll do is we'll start with the current pointer at head, we'll make another pointer previous that will be pointing to null, and we'll say, okay, next pointer will be the next of the current node. Okay, so now what we do is we say reverse the link for the current node. So this link will change and instead we'll have this link. So in current next we'll put previous. Okay, once we've done this, we'll just move all of these 3 pointers, previous, current and next, by one step ahead. So that means the previous pointer will come here where current was, the current pointer will come here where next was, and the next pointer will always be next of current. Okay, and then we just keep repeating the same thing. So in current next, we change the link to make it point to previous node, and then we shift all of our pointers. So if we shift, we'll have previous here now, current where our next was, and next will be next of current. Okay, once again we'll change the link, the next link for current node to make it point to previous node, and we'll shift all of our pointers by one step. So now previous is here, current is here, and next is here. Once again we'll change the link of current node to make it point to previous, and we'll shift our pointers. So now previous is here on my last node, okay, and current is here. Now I don't need to move any further ahead in my linked list. I have reversed my entire linked list. So I can say whenever my current pointer reaches null, then that means the entire linked list has been reversed. And what will be the new head here in my reverse linked list? The new head will be at previous. So this will give me my new head of the reversed linked list. Okay, so when current reaches null, that means my entire list is reversed, and at that time previous pointer will be pointing to the new head of my linked list. So let's see this in code now. We'll create a function reverse linked list where we'll be passing the head of the original linked list. The first step would be to create the 3 pointers. So we have 3 pointers. Previous, that would be pointing to null. We have another pointer current, that will be at head, and we have next pointer. Okay, so next pointer we can make it point when inside our loop. So we'll create a loop, and this loop will run till our current pointer reaches null. Okay, so till the current pointer is not null, we'll keep running this loop where we'll first of all say make the next pointer point to next of current node. And once we've done that, now we can change the link of current next and make it point to the previous node. And now what we have to do is just move our nodes ahead. So we'll make the previous point to where current was, and we'll make current point to where our next pointer was. Okay, so this loop will keep running until current reaches null at the end of the linked list, and when it does, then previous would be pointing to the new head. So we can say our new head will be at the previous pointer, and that's all. That will take us to reverse the linked list. We can either return the head of the reverse linked list, or because we're just passing here by reference, I can just change the head and point it to my new head. Okay, so we've created a linked list here, and let us call the reverse function here, passing the head and then traverse my linked list. Okay, so let's run this, and you can see this is my original linked list, and this is right here my reversed linked list. Okay, so that is how you can reverse a singly linked list. Moving forward to the next question. Let's see, what does the next question tell us to do? The next question says, given the head of a linked list, determine if the linked list is a palindrome or not. Now, firstly, let's understand what exactly is palindrome. So, a palindrome is a sequence that reads the same if you read it from forward or backward. So, for example, if you take this linked list, if you traverse it from the forward or you traverse it backwards, it will be the same. Similarly, if I have another linked list, this will also be a palindrome, because in any direction you try to traverse the linked list, it will be the same, right? So how do I now check if a particular linked list is palindrome or not? Now, one way to do it is reversing the linked list. So what I can do is create a copy of this linked list that is reversed. Okay, so I can reverse the entire linked list, and then if I reverse this linked list, I'll get the same one, right? And can I say if I compare these and these come out to be equal, then I can say that this linked list is palindrome, right? Similarly, if we take a non-palindrome linked list, okay, suppose I take this linked list. If I reverse this, the reverse linked list will come out to be something like this, and these linked list 1 and 2 are not equal, so I can say that this linked list is not a palindrome, right? So that is one way to do it, to reverse completely and then check equal. So basically just doing what we have done in the last two questions. Okay, we first reverse it and then check if it's equal or not. So that is one way to do it. Another way, a slightly better way to do it. So in this solution that we just discussed, we'll have to reverse the entire linked list and check if both are equal, right? So reversing the entire linked list will take O of n time, and then checking if they're equal or not will again take O of n. So another thing that we could do is if we can find the middle point of our linked list, which we have seen in the last lecture how to do that. If we can find the middle point of my linked list and then divide the linked list from there, not divide it actually, but just after the middle point, if I can just reverse half of the linked list, the second half of the linked list. So don't reverse the entire linked list, but just the second half, and then compare it with the first half. Okay, so what I'm saying is, if suppose this is my linked list, so what we do is first of all find out the middle node. Okay, so 4 is the middle node. So starting from the middle node, just reverse the second part. If I reverse this part, what will this part of the linked list look like? It will look like something like this. This is the reverse part. All right, and then I compare the first half and the second part. So what I'll do is, my first half is this and my second half is this. Okay, and are they equal? They are equal. Then that means that this is a palindrome. All right, so basically I'm saying we don't have to check the complete linked list, we don't have to compare the complete linked list, we just have to compare the first half of it and the second half of it, which would be reversed. Okay, so this is something that we can do, right? Because we've already seen how to find the middle point, we've already seen how to reverse the linked list, and we've already seen how to compare if they are equal. All right, so this should be pretty easy. Let's just go through the solution again that we'll be following. Okay, so if this is our linked list, what we'll do is first of all find the middle node. And how will we find the middle node? Using slow and fast pointer. Okay, and this approach basically says that the fast pointer will be moving it by 2 nodes, slow pointer will be moving by 1 node. So when the fast pointer reaches the last node or it reaches null, at that time our slow pointer will be at the middle node. So if we have our slow and fast pointers here, in the next iteration of the loop, we'll have the slow pointer here and fast pointer here. In the next iteration, we'll have the slow pointer here and fast pointer here, okay, on null. So now when our fast pointer has reached null, I can say that the slow pointer is pointing to my middle node. So found the middle node. What I'll do then is, starting from the middle node, I'll reverse the rest of the linked list. Okay, so this I'll call it current node. I'll make previous pointer point to null and the next node point to next, just like we did while reversing. All right, so we'll say change the link of current to make it point to previous. So 3 will point to null, and then we'll move all of the 3 pointers. So now previous is at 3, current is at 1, and next is at null. Okay, and now again we change the link of current node, make it point to the previous node, and then move all of the pointers. So now my current reaches null, and when my current reaches null, that's when I know that I've covered the linked list that I was supposed to reverse, and my previous will be pointing to my new head. Okay, so let's get rid of this now. We just need the new head. So we have one head that is here, that is the original head of my linked list, and another head, let's call it new head, or let's call it head 2. Okay, so head is the original head of my original linked list, and head 2 is the head of the reversed linked list of the second part of my linked list. Okay, so now what I have to do is, if you look at the head linked list, that is 1 3 3 and null, and head 2 linked list is 1 3 null. So basically I'll compare these two linked lists till head 2 does not become equal to null, because the second part of my linked list will be the shorter one, right? So just as head 2 becomes null, I'll stop comparing. Until that, I'll just check if these two linked lists are equal or not. Okay, and when I start checking, I'll see, okay, 1 and 1, they're equal, 3 and 3, they're equal, and in the next chance head 2 will reach to null, and that's when I'll stop comparing and return true, because so far the linked lists were equal. Okay, so again the time complexity here would be O of n only, but slightly better, because here we won't have to compare the entire linked list, but just one half of it with the other half of it, right? So let's try to implement this now. We'll create a function that returns Boolean value, check palindrome, where we'll be getting the head of my linked list and just passing it by value will do. Also, let's add an edge case if head next is equal to null, meaning that my linked list has only one node. In that case, it will be considered a palindrome only, so I can just return true from here. The first step is to find the middle node, and for that let's take two nodes, slow and fast, both pointing to the head. While fast is not null and fast next is also not null, okay, because it can be either of these two conditions depending on we have even nodes or even number of nodes or odd number of nodes. So while fast pointer and fast next is not null, till that time we'll keep moving. We'll move the slow pointer by one step, and we'll move the fast pointer by 2 steps. Okay, so now our slow pointer is at the middle node, and we'll move to step 2, which is reverse the second half of linked list. So my slow is at the middle node, so I'll make the current pointer point to where my slow pointer was, and I'll create another pointer previous where null was, and another pointer next. So while current is not null, I'll say first of all next is equal to current dot next, and now we can change the link of current dot next to point it to the previous node, and now shift the pointers. Previous will come where current was, and current will come where next was. Okay, now at the end of this while loop, we'll have the second half of the linked list reversed, and we'll have the previous pointer pointing to my new head. All right, just like we saw in the last question. So third step is comparing the two halves, and so the first linked list, so the first part of the linked list I can traverse that using head pointer, and the second half of the linked list, for the second half of the linked list I can create another pointer head 2, which will be at current previous node. To compare, we'll start a loop till the time head 2 does not become null, because the second half of the linked list will be the smaller one. So while it does not become null, we'll keep checking. If head dot value is not equal to head 2 value, in that case return false. That means our linked list, the two halves of the linked list are not equal. If not, then we'll just keep moving our pointers ahead. So I'll say head is equal to head next, and head 2 is equal to head 2 next. And if I finish this entire loop without returning false, then that means that the two halves are equal and the list would be a palindrome. Okay, now let's check here with an example. So I've created a linked list here. Let's create a palindrome first, and let's print the result of check palindrome function, where we'll pass the head of my linked list. So this is my linked list and it returns 1, meaning it is in fact a linked list. What if I change it to not a linked list? So now it is returning 0. And let's also check with odd number of nodes. If I have odd number of nodes, this is still a palindrome, so it returns me 1. Alright. So this was the code for checking if a particular linked list is palindrome or not. Let's move forward to the next question, which is, given a linked list, rotate the list to the right by k places. Okay, so what this means is we'll be given some value k. For example, here it is 2, and we have to rotate the entire linked list by 2 places. Okay, so if this is our linked list, if I rotate it once, what will happen is 5 will come at the beginning. Okay, so my linked list, if I rotate it once, it will become 5 will come at the beginning, then 1, 2, 3 and 4. If I rotate it again, then 4 will come at the beginning. So now my linked list will be 4, 5, 1, 2 and 3. Okay, and this will be the linked list when I rotate the list by 2 places. Okay, so this is my output. So you understand now what exactly we're being asked to do. Now we don't have to rotate the list one by one. Okay, we can rotate by k directly by moving the last k nodes in front, right? So if I have this linked list, okay, and the k given to me is 3, then that means that the last 3 nodes, okay, will come in the front of my linked list. Basically this part, last k, these are last k nodes. The last k nodes will come in the front of my linked list. So if I move this to the front, that means 4, 5, 6. And then after 6, what will come? After 6, we'll start again from the head. So 1, 2 and 3. And after 3, I should have null. Okay. So we understand now what we are supposed to do. Let's move to the implementation part. How exactly will we do this? If we are given k is equal to 3, okay, first of all, to move these nodes at the beginning, okay, first of all I need to change some links here. Currently 6 is the last node and it is pointing to null, but after shifting by k, I know that these k nodes will come in the front. That means what will come in the next of 6 will come my current head. Okay, so number one step would be find the last node and make it point to head node. Okay, so for example, I find out that okay, 6 is my last node. So 6, I'll make it point to my head, which is 1. Okay, so now this is what is called a circular linked list. So now the last node is basically pointing to the head node, and there is no last node in my linked list. None of the nodes are actually pointing to null. So we don't know where this linked list is starting or where this linked list is ending. Okay, I mean, we know where it's starting at the head node, but that's not where it should start, right? So where should it be starting? It should be starting here at 4, and where it should be ending? It should be ending at 3. Now, how do I know? Let's first take care of the ending part. How do I know where it should end? If the length of my entire linked list is n, okay, if I have n nodes, and if I'm moving the last k nodes in the front, then my last node would come out to be the n minus kth node, right? Because the rest k nodes will come in the front. So n minus kth node, which is here 3, would become my last node in my rotated linked list. So another thing that we need to do is find n minus kth node and make it point to null. Okay, so now this 3 is pointing to null. Now the only thing that is remaining is the head. Where will the head go? The head will be here, the last kth node, the kth node from the end. Okay, so the kth node from the end, I can either check that, I can either traverse the linked list in reverse, but that is a bit complicated, or else I can just say that this is if 3 is my n minus kth node, then 4 is my n minus k plus 1th node, right? N minus k plus 1th node. So before changing 3's pointer and making it point to null, before that I can make a pointer and say, okay, this is my new head. Okay, so what I'm saying is this will become, so what I'm saying is that this will become my third point. This is my third point, and this will be my third step, and the second step would be find n minus k plus 1th node and make it new head. Now is my new linked list ready? If you see, the new head is here at 4. That means here is where, this is where my linked list will start at 4. So 4, 5, 6. After 6, I have 1, 2 and 3. 3 will be the last node. Okay, so if I write this properly, this is nothing but the same as this. Okay, so I have my output. So basically I have to do three things. First of all, I have to find the last node, okay, and make it point to head. Then I have to find the n minus k plus 1th node, and for this I'll also have to find n. Okay, so we'll have to find the number of nodes in my list. That I can do easily, just like we traverse our entire linked list. We can find, while traversing, we can make a pointer and just keep increasing our counter to get the total number of nodes in my linked list. And once I have the total number of nodes, that will be my n, then I can calculate n minus k plus 1th node, where that will be residing, and make it point to my new head. My new head is ready, and last step would be make the n minus kth node point to null, so that I know that's where my linked list ends. Okay, now a few things here. First of all, this we can combine when we are trying to traverse the entire linked list to find the last node. In the same step, we can find n, okay, because here for finding the last node also we'll have to traverse the entire linked list, and for finding the number of nodes, total number of nodes, we'll have to traverse the entire linked list. So both of these steps we can do in the same loop. Okay, and after that, if we can just find the n minus kth node, I know that the next of it would be n minus k plus 1th node. Okay, so I don't have to loop till n minus k again and again. Third thing, I'm trying to find n minus k here, but what if, okay, what if k is more than or equal to n? What if k is more than equal to n? So what if k is more than equal to n? So try to understand this, okay? If I have a linked list which looks like this, okay, now, and my k value here is 4. Okay, let's just take 3 elements. My k value here is 4, which is more than n, which is the number of nodes. So what will happen is, when I rotate it once, 3 will come in the beginning. Now for k is equal to 2, 2 will come in the beginning, and for k is equal to 3, again 1 will come in the beginning. So this and this is equal, it's the same linked list. So basically, if k is a multiple of n, then after rotating, the linked list will look the same. If k is a multiple of n, after rotating, it will look the same. And if not, if k is more than n, okay, so for k is equal to 4, what will happen? Again 3 will come in the beginning. So now this and this is equal. What we were getting at k is equal to 1 is the same that we are getting at k is equal to 4. So that means we can find out the actual value of k should be k modulo n. Okay, so for example, if here k is given to us 4, I can say k's real value, the real number of rotations that we'll have to do, that will be equal to 4 modulo 3, that is equal to 1. So 1 is the rotation that I need to do, and not the original k that was given to me, which was 4. Okay, so while solving, we'll take care of this. We'll find the actual number of rotations by using this formula, k is equal to k modulo n. Modulo here gives us the remainder when k is divided by n. Okay, and if k is equal to, after this, if k comes out to be 0, if the remainder comes out to be 0, then that means it requires no rotations. Okay, so that would be the solution of this question. Let's go forward to the implementation. So void rotate by k, and here we'll be getting the head of my linked list, and I'll get some value k. Okay, so first of all, let's check the value, get the actual value of k, the actual number of rotations that we'll have to do. That will be equal to k is equal to k modulo n. Okay, also we need to find n first because that is something that is not given to us. Okay, so let's say node star temp is equal to head, and I'll make a variable int n is equal to 1. Now while temp next is not equal to null till I don't reach the last node, basically I'll keep increasing the value of n, and I'll also keep moving temp pointer to next. Okay, so now here we have the value of n, which will give us the total number of nodes, and also temp will be pointing to last node, right? Because when temp will come at the last node, that's when temp next will become equal to null and the loop will break. Okay, so now we have the value of n, so we can find k is equal to k modulo n, and if k comes out to be 0, then I can just say return, right? Because I don't need to do anything, then it will be the same list that I currently have. Okay, so if this does not happen, what we need to do, we already found the last node, so we make the last node point to head. Okay, so the first step, which is make last node point to head. So last node is currently being pointed to by the temp pointer, so temp next is equal to head. The second step, find n minus kth node. So for that we can create a loop. Okay, and let's create a pointer as well. We can use the reuse the temp pointer actually, make it point to head, and then I can create a loop here for I is equal to 1, I is less than n minus k, I plus plus. I'll just keep moving temp pointer ahead. So at the end of this loop, now I have the temp pointer pointing to n minus kth node. Okay, temp is pointing to n minus kth node, n minus kth node, and my new head, where would that be? My new head will be at the n minus k plus 1th node. So basically my temp next will be my new head. This is the n minus k plus 1, this node. Okay, so I have my new head, and the third step was make n minus kth node point to null. So I can just say make temp next is equal to null. So second step was find n minus kth node and make next node as new head. Okay, so we did that here, and we made the n minus kth node point to null. Okay, at the end we can either return the new head of my rotated linked list, or I can just say head is equal to new head. Okay, so now the head pointer will be pointing to where the new head is, and let's test this. Rotate by k, where I'm passing my head and I'm passing k is equal to 2. So you can see here, this is my original linked list, and by rotating the list by 2 steps, this is my output. Okay, if I change k value to 3, then the last 3 numbers 3, 4, 5 will come at the beginning, right? So looks good, and you can see if I pass k value equal to n, nothing happens. If I pass k value more than n, 6, then only that is equal to passing k is equal to 1. This is how we rotate a linked list by k steps, and the time complexity of this would come out to be O of n, right? Because we're traversing the entire linked list to find the last node and also to find the number of nodes in my linked list. Let's move to the last question for this lecture. This question says we are given two sorted linked lists and we need to merge them into one single linked list such that the resulting list is also sorted. So sorted meaning all of the elements in my linked list, all of the values in my linked list, they are sorted in ascending order. So you can see in the list 1 that I have, all of these values are sorted 1, 3, 5, 6, and in the list 2 as well, these values are sorted 2, 4, 7. And now what I need to do is combine these two linked lists into a single linked list such that the combined linked list is also sorted. So my output should look like this. Okay. What comes to my mind is one way to do this is, for example, if I have these two linked lists, okay, and I need to create a third combined linked list. Okay, so what I can do is I can check what is the smallest number. So the smallest number in these two linked lists would come at the beginning of the linked list, right? Because these two linked lists are sorted themselves. So the smallest number either would be the first number in my first linked list or the first number in my second linked list. So I just need to compare these two numbers to find out the smallest number in my combined linked list. So let us take two pointers, head 1 and head 2, that we will be using to compare values and find out what value will come first and next and so on. So when we compare head 1 and head 2 value, I see that head 1 value is smaller. So I can safely say that this head 1 value is the smallest number that will be coming in my combined linked list. So now that I have established that this is the smaller number, what I can do is I can create a new node with the same number, right? I can create new nodes with the same values, with these values, and that will create an absolutely new linked list for me, but that would be taking up some extra space if we are creating a new linked list. We can also, what we can do is just change the links in these linked lists to create a combined one. So how can we do that without creating new nodes? Okay, without actually creating new nodes, how can I just combine these two linked lists? So to do that, let's first take a dummy head node. So we'll take a dummy head node, okay, with some random, value -1 or 1000, -1000 or something. So we'll have some dummy head node, and this dummy head node, in front of this dummy head node, will actually start our combined linked list. Okay, so when we find out from head 1 and head 2 which of these two are smaller values, smaller value is 1. So in front of dummy head node, let's also create another pointer head 3. Okay, that head 3 will be used to traverse the combined linked list. Okay, so head 3 will make it point to 1. Okay, because we've established that that is the smallest number, so it should come in the front of our combined linked list. Okay, and now what I need to do is I'll move the head 3 forward, the head 3 pointer, and also move the head 1 pointer ahead. Okay, because I've already covered this number, so I'll move the head 1 pointer ahead. Now again, now I need to find the second smallest number that will come in my linked list. So again, the second smallest number either would be at head 1 or head 2, right? I compare these two values 2 and 3 and I know that head 1 is pointing to the smaller number. So in front of head 3, I put 2. Okay, and again I'm shifting my pointers. So head 1 will come here and head 3 will come here. And now again I compare head 1 and head 2 values. Now out of head 1 and head 2, I know head 2 value is smaller, 3 is smaller. So in front of 2 I will have 3, right? And now I will move head 2 pointer forward and head 3 pointer. Alright, now again we compare head 1 and head 2. Out of head 1 and head 2, I know head 2 is smaller, so we make head 3 point to the smaller value, which is 4, and we move the head 2 and head 3 pointer. So head 3 will come here and head 2 will point to null. I cannot compare head 1 and head 2 values because head 2 has become null, right? So whenever any of these pointers, head 1 or head 2, when any of these pointers become null, that's when we just say make head 3 point to head 1, okay, which is not null. So what I'm basically saying is, if out of head 1 and head 2 any pointer becomes null, so we know that that linked list has ended there. So in front of the head 3, which is keeping track of the combined linked list, we'll just put the other linked list which has not ended yet. So here head 1 linked list had not ended, so we'll just put head 1 in front of head 3. Okay, and this will be our combined linked list, and we can say that the combined linked list head would be given to us by dummy head node next, right? This is dummies next. This is the dummy head node, and the dummy head node's next pointer will give us the head of the combined linked list. So once again, I'm trying to explain to you. Okay, you already have understood what exactly we're doing here, right? We're just comparing the value starting from the front, where of the two linked lists, we're comparing the values, and whatever is smaller, that I'm putting in my combined linked list. But what you really need to understand here, that we're not creating these nodes again. What I'm actually doing is, when I'm comparing 1 and 3 and I know that 1 is smaller, I'm just making dummy head nodes next point to 1. And then when I'm comparing 2 and 3, right, so I'm just making 1 point to 2. And when I'm comparing 5 and 3, I know 3 smaller, so I'm making 2 point to 3, then 3 point to 4, 4 point to 5, and 5 is pointing to 6. So this is how I'll get the combined linked list with 1, 2, 3, 4, 5, 6 values. So we're just changing the links here, and on what criteria or basis are we changing? We're comparing the values starting from the start of the two linked list. Why? Because these two linked lists are themselves sorted. Okay, so the smallest values would be present in the beginning of my linked list, and if one of the linked list reaches null, like for in this example, I reached null, head to reach null, meaning this linked list is empty, does not have any more nodes to compare. So I'll just put rest of the other linked list in my combined linked list. Okay, let's see this in code so that it's more clear. So we'll create a function here which will return the new head of the combined linked list. So node star merge linked list, and we'll be getting here the heads of two linked lists. Okay, let's call them head 1 and head 2. So the first thing we need to do is create a dummy head node, and I hope it's clear why we are creating a dummy head node, so that we can create the combined linked list in front of this dummy head node. Okay, and let's create a pointer as well to traverse the combined linked list. Let's call it head 3, which will be starting from the dummy head node. Okay, so now while head 1 and head 2 are not null, what we'll see is we'll first of all check if head 1 value is less than head 2 value. If head 1 value is less than head 2 value, then that means head 1 will come first, like the node which is being pointed to by head 1 pointer will come first in my combined linked list. So I can say head 3 next would be head 1, and then I can just move the pointers ahead. So head 1 is equal to head 1's next. Else, if head 2 value is less, in that case I'll say head 3's next should be head 2, and head 2 will be moved forward. Okay, and at the end of this if else, we'll also move the head 3 pointer ahead. So head 3's will be head 3's next. This loop will end when either of head 1 and head 2 becomes null. So again I can check if head 1 is not null yet. So I'll say head 3 is equal to, or sorry, I should say head 3 next is equal to head 1. And if head 2 is not null, then I'll say head 3 next is equal to head 2. Alright, and the new head node would be given to me by dummy head node next, right? That's where our combined linked list would be starting. So let's check this. Taking an example, we've created a linked list here with the values 1, 2, 5, 6, another linked list with the values 3, 4, and let's call our function merge linked list, where we are passing head 1 and head 2, and this function would be returning to us the head of a new linked list, combined linked list. So we can call the traverse function on that to see the combined linked list. So you see here, this is the first linked list, the second linked list, and this is our combined linked list which has the sorted values. Okay, so that's how you sort two linked lists such that, you combine two sorted linked lists such that the combined result is also sorted, and the time complexity here would depend on whatever will be the length of my shorter linked list, because that's what we're traversing here in the while loop. So if it is n, so O of n will be the time complexity for our solution. And that's all for this video. Thank you so much for watching. Do practice all of the questions that we discussed in this module, and if you have any doubts, drop them in the comments so that we can get to them.